for the first talk,
I'll just take
AI in robotics, autonomy in robots.
Thank you very much. Oh, good. How do I click?
Yep.
And I also start the videos like this?
Sure. Okay. There's your screen.
Good. Perfect. Thank you very much for joining. So as we probably have an audience here that has not heard of us yet, I will show you a couple of slides, maybe 7, 8 slides about us as a company who is Micropsy Industries, and then I will show you some use cases so that you also have an idea of, okay, what do we actually do? How does it look like when a robot moves, guided by our AI system? I call this presentation Autonomy for Robots, Tackle Variance in Production. We want to give some autonomy to the robots. We, of course, do that also with AI, like probably everyone nowadays does with AI. I will say it up front already. We have in the hall 10, in the very front, we have a booth, so you can come around later to take a look at this, what I'm showing here in real. Why do we say tackle variance? We are helping companies to automate where they hit some borders or some limits where they actually cannot automate anymore because they say, well, it's just too difficult. If that's a typical example that the customer would bring us where it says, okay, it's hanging on some rack, I need to pick this part, I need to insert it, and then this one is hanging here somewhere. It's hard. For the human, it's super easy to insert it also, but for a robot, it's almost impossible. And this is very typical for what we do. So, first, some minutes about the company and who we are. My name is Maximilian Mutschler. I'm responsible for the sales and engineering team. We are a Berlin-based company. Here's a picture. Actually, this gentleman in the middle, Ronnie, you see him standing at our booth also. But this is the first employees from many, many years ago. Most of them are still in the company, but nowadays we're around 70 employees. So we call ourselves still a startup, but we're a little bit bigger than the typical startup. And what we do is actually we make software. So what we really do is software, and this software helps to combine AI and industrial robots and gives them a hand-eye coordination. We're a team based mostly in Berlin, like 50 people in Berlin. The rest of those 20 are in the US and in Japan. Why am I showing you this customer slide? First of all, to say, okay, we are real, yeah, we exist in production. This is not updated, this is old, but still just to show, okay, there's real customers already who use our product in production. We are mostly active in automotive sector, typical German, American. Then there's a lot of electronics, but also household goods, especially fridges, white goods, appliances. And then, of course, a little bit in other industries, in research and so on. What's the typical challenge? I think I don't need to explain that very long or in detail, but the big challenge is that many parts in manufacturing are already automated. Like typical example, yeah, building cars, welding, screw driving those cars, 100% automated. But all these tasks must be geometrically understood, must need to be fully understood, need to be the same. Very often the robots are not equipped with sensors. But the expectation is that yeah, all of this can be automated. But the reality, if we're looking inside the car especially, is that there are still many human workstations. These human workstations are necessary still because the applications are very complex. That means, like I just mentioned, this cable, it's just hanging somehow. For us humans, that's super easy because we have eyes, yeah, we have hand-eye coordination, and we also have amazing end effectors, and 2 of them. So we can just quickly adapt. Although this is a different piece, I can also hold it. Robots don't have that by nature. So what we want to give the robots is the hand-eye coordination. And we do that actually in real time. I will show that later. How do we call our solution Mirai. So Mirai is actually in many Asian languages, it means something like the future. So it's different pronunciations, Mirai. But what we call it, why we call it Mirai, it's because it's Micropsy Industries Robotics AI. What you need is a robot, some kind of a vehicle. We need a 6-axis robot. We need also some cameras for input of the signal, and the signal for us is the camera image. And then you have the end effector, depending on the application. Why do we call it autonomy within bounds? Because we want to make something which is still controllable. So you still have it under under control what's actually going to happen with the robot, because AI for many people is still a term which might frighten them. It's not very specified. What does AI actually mean? So we do this within bounds because we want to control the training. So the training of the skill, we call it a skill, is in the end the ability, needs to be within a certain time frame, and we don't want it to learn something that is not desired, like it could happen in reinforcement learning. So what we do is imitation learning, and it can be very, very quick. Within 15 minutes you can train a skill where later the robot will always find this plug, although it's in a different position. What are typical use cases? Typical use cases are for us something related with cables, with sockets, yeah, cable plugging or connector plugging. Then also insertion assembly tasks. So we focus a lot on assembly because in assembly you will often find a part that needs to be picked and then placed somewhere, and that needs to be very accurate. Rack hanging. Rack hanging is something where we also showcase a demo on the other side of Hall 10. Because you might know that there is some companies where some metal pieces need to be coated, need to be painted, whatsoever, and there's a human worker standing, putting metal pieces on hooks. That's also something that we do. It can be even on a slow-moving conveyor. Screw driving, very typical example. Sometimes the screw is in a different position, or the part is in a different position. Leak detection, I will explain that in a video. And also simple pick of very glary objects, for example. All of them have in common that they have variances in the position of the part, in the color of the part, in the shape, in the form, or maybe also in lighting and background. So very important. For many vision systems, it's a struggle that lighting can vary. Sometimes there's light coming in from the side, sometimes artificial lighting, sometimes not. We can just train that. So let me show you some use cases. Time-wise, 7 minutes. Now we have 10 minutes left. I will show you some use cases. That's probably the most interesting. So, there should be a video starting, but if not, then we take the next one and we might go back to this. Okay. This is a use case that we have automated for BSH, Bosch Siemens house appliances. You all know a fridge. At the back of a fridge, there's a compressor. In this compressor, there's some gas, and that's necessary for the cooling. And this gas should not leak out of the soldering areas or the crimped areas of these copper pipes. The issue is that these copper pipes always are at a different position. They are soldered, so there's a different color, a different shape also of the soldering area, but that needs to be checked. And it needs to be precise. Right now, there's a human worker standing with a gas probe and just checking these spots, but that's very prone to errors and also a very tedious task. So let me play that quickly. I will not play the videos in the full length. You can find them on our website. You can see over there where we are a little bit more, but just to give you the real impression. So this is how it looks after it's automated, and here it's before. A human worker has to check these spots, but they are always at a different spot. That's why it's so difficult to automate, and companies have tried this with 3D scanning, with other vision technology, but they couldn't succeed. Here you see actually a training where the human operator just trains the robot. Okay, this is what you need to find. That's the spot that you need to see. And after doing this, it takes them now an afternoon to train a completely new application for a new line of fridges. Actually, you see that Mirai is now locating always the correct spot. There's always a handover between robot, hard-coded robot system, and then the Mirai part. But this is running 24/7, and now they even find more failures in those fridges. You see that, okay, now we're approaching, this is the Mirai part, finding this spot. And you see it over there again. This soldering area doesn't look very neat. It's always a little bit different in shape, color, and position. Next one, very typical. Often we cannot show the real videos. Bosch Siemens was so nice to allow us. If I would ask now the automotives to show the videos here, they would not be happy. But it's the same thing like this. Handling a cable, especially a free-hanging cable out of the air, and then inserting into the socket. And here you see quite nicely that always when the light is on, we are active. When the light is off, it's just robot program. So here the colleague is actually pulling away the cable, not because you would do this in a factory, that you pull away the cables from the robot, but just to show it's very robust. It doesn't need to be in the predefined position. and then it's also inserted in the correct slot. So again, here we find the cable until he holds it still, then the robot can actually pick it, and now also insert it. Here the light goes on again, and for the insertion also this is AI controlled. The laptop is not standing at a fixed position, he also turns it now again just to simulate in the real factory conditions where parts should be almost at the same spot, but they still might vary a little bit, even if it's just a millimeter. You would need the accuracy to actually insert the cable at the correct spot. That's what we guarantee, that's what we make sure. And one more comment, you see now two cameras. Those two cameras don't create a 3D image or anything, they are just creating 2 times 2D. We work with extremely simple pictures, and all the rest is in the software, the difference, because we don't take measurements. I can explain a little bit about that later, but the big difference from us to all other vision cameras, at least what we've seen and what we still see, is that vision cameras always take a measurement. They scan an object, they measure it, compare it with the CAD data, and then send the robot to an offset. We don't do that. Yeah, one more, hook hanging, wrench hanging, if you want to call it this way. As you see here, the colleague has just simulated a task that we also saw at some customers, and we have a little conveyor belt, and we need to always hang this wrench on the hook. And by the way, this is now a lot of universal robots. We're also compatible with KUKA robots and FANUC robots. But just to simulate, the hook can vary, the wrench can vary. We pick it first and also make sure we hang it on the correct spot. And here it's also, again, movement, but there's a real-time tracking, so Mirai, our software, enables the camera to find the object in real time. Yeah. And this is done with a very small UR3 robot, so the reach is very limited, so good job from him that he actually managed to complete it there. Okay, how do we work? What's our commercial approach? Also to tell you a little bit about this before I ask for questions. We work with a method called customer success planning, so you will never have only the sales guy working with you. If you are interested in finding a solution, you will always have an account manager, that's somebody like me, then a product manager, and also an automation engineer to evaluate together the projects. We focus on target accounts. We deploy Mirai in production together. We do only scalable projects. So if you say, yeah, that sounds all cool, I have one robot maybe where I could play a little bit with AI. Unfortunately, we are too small to do that because we also need to be efficient with our resources. We say, let's find something where we both benefit from. But then if we agree on this, we hold your hand instead of letting you go and try alone. This picture down low is a beautiful cooperation that we have between KUKA, Mercedes-Benz, and us. And yeah, there's a mixture of different employees there from different companies, which shows this strong bond. Thanks a lot for the time. I can answer some more questions. I have some more backup slides if necessary, but I wanted to keep it short and mostly focused on some real examples of AI on the robot in motion. Thank you.
Thank you, Max.
And again, our booth is over there in the other hall. I'm just repeating that if you want to come around.
Do you have questions? I have so many questions.
Happy to take yours also.
Okay, yeah. So what does the accuracy look like? Because this is just
accuracy.
Very
so how precise can we be?
Yes, yes.
So what do you think is my answer? Because it's always the typical answer.
I am expecting your... yeah, of course.
It depends. Yeah. And what does it depend on? It depends on the optics that we use. Because the beautiful about our system, or the beauty of our system is, you just see this camera over there. It's now a Ximea camera. We're also compatible with Gig-E cameras from Baumer, for example. Oh, but you see this camera,
yes.
And we just have a Fujinon lens on it. So if you say, I want to lift a car door, we use a wide-angle camera. But if you say, I want to insert a needle into a little ribbon, which we also do, then you would use a 50 millimeter, 100 millimeter magnification camera. So it really depends on what you need. And the answer is, and the correct answer is, the accuracy is 1 pixel. Yeah? Because 1 pixel of the resolution that we see is in the end the accuracy that we can reach, and it depends on how big is the pixel. And it also depends on the training. I didn't say anything now about how do we train this, because the training is super easy. It's radically different from what other cameras do. But if you're interested, I can show a little bit more about that also on our booth.
Yeah, that would be really nice, because this is extremely cool what I just saw, and it was like, because there are so many variables as well. So there is orientation as well. So in your laptop and USB cable example.
Yes.
So there's definitely, I mean, it's not so complicated, the orientation for a human at least, but if you understand, I mean, the robot could have really done it vertically, or could have at least tried, but it did not even try.
So there's always this. Let me explain again that we only take care, and this is a lot of show. Yeah, what we do here doesn't really look like production. That's also showcase to impress people, and then later tell them, okay, but if we make this production ready, you will hardly see what we do, because it's a very small correction only. So there's always a handover. So we would, if I want to pick this, you would know roughly where it is. It's either here, there, or there. So I would have the handover pose here, and then only let Mirai correct this little part. Yeah, only let this little correction, or let me call it like this, correct like this. So there's only a very small part that we, in the end, actually really correct.
Okay, and also at the insertion level. I mean,
again, could have. Once you know, okay, my object, my target is somewhere down here, and I'm holding this plug now.
Yes.
You will not let start Mirai here and look for it and look for it. That doesn't make sense. Yeah. You would know, okay, it's somewhere here, and I just let it correct for this last centimeter or last couple of millimeters. Yeah.
Sure. I mean, okay, I think we still have 4 minutes, and I think for the live broadcast, we really have to start at 20, the next one.
No problem.
But I can keep going. This is my field. I personally work with standards. Also, OPC UA for robotics is also one of the things that I have to do. So this it's extremely cool what you guys are doing there, and I'll definitely go to your booth after the show, after this session. But really cool. But you said skills, right?
Yeah.
But what I have heard the term skills quite a lot. And when we talk about skills, is it something that you can just bring together and then just start, or?
Yeah, so we always have, for the robot platforms that we're integrated with, and that's only 3, because that was driven by demand. It's a lot of work for us to integrate, because we need a real-time interface to talk to the robot. We don't just send him on an XYZ coordinate. We need to talk to it in real time. So there's always, for the platforms where we are integrated, there's for UR, it's called a UR cap. For KUKA, it's called a COP file. Basically, it's a plug and play. So you will not feel as a user that there's a lot of stuff done in the background. But yeah, correctly. So that's what we do. There's a plugin directly.
Perfect.
I can, if you want, I can, and if there's 1 more minute to fill, I can actually. It's not a beautiful slide, but I believe it's a quite important slide, showing the differences to normal cameras again. Because I just want to highlight again and again, we don't take measurements. That's such a big difference, and it then allows us to handle much more complex parts. It allows us to handle parts with black on black, white on white, a black hole on a black part, a mirror on a transparent surface, whatsoever. It really doesn't matter. As long as the human can see it, we can do it. We don't take measurements. We don't take measurements. We don't take measurements. So that means it's really, really important to emphasize on that, because that's the big difference to all other systems. And that means also that the path planning is during the execution. So actually, we only do relative movements, and we can adapt the path while we are approaching the object. That means sometimes it's vibrating, sometimes it's hard to do a good scan or a 3D picture of such an object. Yeah, it's very, very difficult, and these are things that we can actually take care of. So should I say more?
I mean, if you have more to share, you can always share more. So is it based on point clouds then?
No, not at all, exactly. So we don't take any CAD data, point clouds, no measurement. We just scan the real object as it is. And we actually work with very low resolution. So the image that we take, usually our users are surprised that they say, okay, that's the image that you work with, and you can achieve the accuracy. It's 300 pixels times 250 pixels, so it's really, really, really small, but it's still enough for accurate execution. I can check what else. I would have some more examples here. Yeah, that's maybe. Oh, why is there no video? There's no video. There would be more contour following, following the contour of a sealed bag, for example. It's not a video, it's not playing right now, unfortunately, is it? Ah, it is.
Nice.
Yeah, I will just show you some more. Until you say the time is up and we
It is. I mean, I can already welcome the next speaker, but thank you for your time. It was
Thank you very much.
But you'll see me soon.
Cool. Thank you.
Thank you so much. So the next one, inside view of Bergkristall sensor and web inspection solutions with contact image sensors. Andrea Fant.
Nick first. Nick first.
So the third one first?
I'm not sure.
We are together.
This is this one or the one that I just...
Yes.
The last one?
No, this one.
Yeah. So you go on.
Okay. Yep. Thank you.
Thank you.
Okay. I want to talk about our latest product, the Bergkristall contact image sensor, delivering much better data, much more information than has been possible in the past. First of all, I want to tell you about the history of the Bergkristall. Then I'll give a short introduction on what we can do in the future with this product. I'll give you an introduction to the FPGA framework that's essential for the overall function of the sensor, including LED multiplexing, which is a very powerful technique, especially for things like shape from shading, also known as photographic stereo. I'll talk shortly about the relation between trigger precision and color matching that you can achieve with different sensor topologies. Give an introduction to the basic sensor structure, the regions of interest that we support, shape from shading technique, and an outlook on hyperspectral imaging and true color imaging. Vision has introduced CIS technology for industrial applications back in 2001. The improvements we introduced over office scanners back in 2001 were larger working distance of 10 mm and more, line rates of up to 90 kHz, a rugged industrial housing and a 24-volt DC power supply, industry standard interfaces such as CameraLink or Gigi at that time, improved illumination like coaxial light, large width scanners with modular design up to 2 meters, 3 meters, 4 meters, and the shading correction done in hardware to release the software from doing shading correction. In the following years, we added staggered zero-gap sensors with geometry correction. What we do is that we stagger the sensor chips to create overlap, and with support of a FIFO, we can get a complete gapless line, while the conventional inline sensor has gaps between chips and larger gaps between substrates. We used LED multiplex to create multiple images from a single sensor, and we introduced switchable resolution so that the sensor can switch to any resolution from 1200 dpi down to maybe 50 dpi, or 20 micrometer pixels up to 0.5 millimeter pixels. During the last years, during the last decade, we got continuous customers complaints because they want higher speed and higher resolution. So we started with the development of a sensor chip with an advanced 5-transistor pixel cell for best image quality. The 5T transistor cell gives us two advantages. One is lower noise and lower crosstalk, better black level, and the other advantage is that we can interleave illumination and imaging even better than in the past. The next goal was to get 1 megahertz line rate, 1000 kilohertz, to get a 12-bit grayscale resolution, and to have a 1200 dpi pixel field. I explained the applications later, plus an additional single 4800 dpi line. 1200 dpi is 21 micrometer, 4800 dpi is some 5.5 micrometer. And we requested on-chip digitization and a direct FPGA interface to keep the system simple and cost effective. This sensor can only be reasonably used together with an FPGA backbone. The FPGA backbone supports things like advanced trigger control for applications requiring start-stop. If your conveyor belt regularly stops between pieces, need to handle this. An integrated illumination controller that supports multispectral imaging and that supports shape from shading. 1D and 2D regions of interest, so that the huge amount of data that our sensor can deliver is limited to the regions of interest our customer needs right at the front end, and binning to the required resolution, so that our customer can choose any resolution from 4800 dpi down to 200, 175 dpi. Let me talk shortly about LED multiplex. Most color sensors that you know have one or another form of a color filter put onto the chip. This may be a primary color filter passing on 1/3 of the photons to the sensor, or a complementary color filter where you can pass on 2/3 of the incoming photons to the sensor. There are also CIS sensors in the market with the color filters. We do not use color filters. Instead, we use LED multiplex, meaning that if we build an RGB camera, we make a red flash, read the data in, make a green flash, read the data in, make a blue flash and read the data in, and then combine the 3 lines read into a single line output to the frame grabber. The LED multiplex has several advantages. The first, you are completely free with the color model. We can use 3 flashes, we can use 8 flashes for a hyperspectral camera. We can use 4 flashes for shape from shading as we do it. We can use a single flash and have a monochrome camera. The same chip and even the same device, if you use a subset of the existing illumination, lets you create several images, and the images are correlated to each other with pixel precision. Another advantage is that the multiplex may also be applied to illumination geometries instead of colors. Meaning, we can make a front light image with a red, green and blue combination, as well, and with the same sensor a backlight image with red, green and blue. This is used in Germany, for example, to recover documents that have been shredded into complete documents with two-sided inspection with a single sensor. The same thing can be done for multispectral imaging. The best thing is the operation is LED multiplex is table driven. The table is set by the user of the sensor. The correlation, in practical applications, you always have a line trigger which is driven by the belt or by the motor or whatever moving mechanism, or by the drum, whatever moving mechanism you have. If you use color filters and separate lines, typical would be 8 line spacing, then you need a FIFO for compensating. The object on inspection reaches the red line first. 8 lines later it reaches the green pixels, and then 8 lines later it reaches the blue pixels. On the electronic side, you need a FIFO, maybe in hardware, maybe in software, that compensates this delay and joins the matching lines. Now this requires, the ones among you who have already used TDI know that with multiple line setup, triggering is very, very critical. The trigger fluctuation that's permitted with such a setup is 6% only before you start matching one line, matching line 16 of red with line 17 of blue. So this requires very high trigger precision. A solution with a single flash, a single line that's multiple flashed, is much more resistant to trigger fluctuations without distorting the image. Okay, I want to give you a short view onto the sensor structure. On top you see the LED boards that come in segments. Below you see the sensor boards. The sensor boards are connected to FPGA boards, and FPGA boards provide video output paths. A central controller board, the bottom left, controls the trigger, triggers the sensor boards and drives the light sources. A power supply distributes the power evenly among boards. What you see here is that you can share data between boards. So we can shift video data from one FPGA board to the next and output them through a single output. This is helpful for customers who do not have the processing bandwidth and work only with regions of interest. Regions of interest, this is a typical application from security print. This is a banknote dummy. Everything else is, I think, forbidden in Germany. And if you look at the banknote, then there are actually only 4 or 5 regions of interest that you want to inspect for safety. And these regions comprise an area of maybe 3 to 5% of the total banknote area. So if you, like we do it, support 2-dimensional regions of interest, as I have shown it here, you can cut the amount of data inside the sensor to 3 to 5%, which means you save on cabling, you save on frame grabbers, you save on PCs, you save on processing power. So 1 and 2-dimensional regions reduce the workload for the machine vision system. Shape from shading or photometric stereo is another application for multiplexed LED. What you see here is a pharma package. On top you see 4 raw images created with shape from shading, meaning you light from the left, you light from the right, you light from top, you light from bottom. The 4 images are appear more or less identical to the eye. If you apply standard algorithms, then you get a gradient X image, a gradient Y image, a height profile, and an albedo profile which contains color information but no 3D information. The image on bottom shows the extracted height information converted into a 3D view. So you can really extract any tactile phenomenon like here for blind people. Banknotes must be recognized by blind people. A pharmaceutical package must be read by blind people. And these tactile features required for blind people can be brought out very clear using shape from shading. Okay, last foil is the Bergkristall sensor, as you will explain later, has also been designed for hyperspectral imaging. If we combine, the Bergkristall chip supports 48 active video rows. Combined with a dispersive element, it could be a prism, could be a grating, the sensor will deliver spectrally resolved lines. Due to the high speed, we can deliver 20,000 full spectra per second, meaning we can run 20,000 spectra per second. With 300 dpi resolution, this means we can do inspection at 100 meters per minute with full spectral resolution. To handle the bandwidth, we will include a converter that's customer programmable inside the sensor and deliver only the true colors red, green and blue. So again, data reduction at the front end. Okay, Andrea will continue outlining the chip behind the design.
So I will show you how the chip is built inside. It's a nice opportunity for me for the first time to show what we do in silicon together what is done in application. Normally these worlds are disconnected. So this is the silicon that we have developed for Teach Hour. It's a pixelated array, 1.5D sensor, it's called like that, with 52 times 876 pixels, plus 1 row at 20 micron, plus 1 row at 5 micron of dimension. And we allow full external addressing for the row, so we can control each row exposure, reset, conditions independently. We read out the value of the pixel in an interleaved way, so we can pretty much pipeline the conversion to get these 1 million rows per second readout that is needed for the application. We can change the ADC resolution. We have an ADC on board, so we can change the resolution between 8 and 12 bits. And the technology we use is 180 nanometer and with 5 metal layers. Just to go into the details, the presentation is higher level. If you want more details, we can discuss. Also, we implemented a multiplexing from 8 to 1 channel exactly for the reason that was just mentioned, to do data reduction when possible. The sensor is about 20 millimeters by 5 millimeter. The sensitive area is almost as wide. And you see in a block diagram, you see the pixel array is on the top. Then we have a huge amount of ADCs. It's pretty much double than the number of columns of ADCs. Each ADC converts a portion of the image, pretty much a vertical portion of the image, and it sends the data to the digital part and at the end to the output drivers and the output multiplexers. How did we implement the dual resolution? This is a zoom in of the pixel array on one corner of it. We have a region where we implement the 2400 dpi resolution, so this is 20 micron pixels. And we have a region where we implement the 4800. They are interleaved, so they are supposed to get exactly the same alignment, exactly the same image quality, exactly the same lighting. The pixel we used is kind of standard. It's just slightly different from a 40. It's a 5T, where we allow also the reset of the floating of the photodiode itself. So that we are sure that we can keep a row in reset constantly, that doesn't get any bleeding to the neighboring rows. And we can implement a rolling shutter and global shutter as needed by the application. The ADC, it's a bit going to detail, it's a single ramp ADC, so it's normally used for, let's say, no extreme resolution, 8 to 10, 11 bits or so. You use ramp ADCs. First you convert the reset level, then you convert the signal level, so the exposed level, and you do the difference between the two, and it gives you a CDS, a digital CDS. Or you can do a CDS analog in advance, so you sample the value of the reset, you subtract the value of the signal, and you convert that directly. So all these modes are supported. The ADC is implemented in a 10 micron pitch, so we use 2 ADCs per column, and this ADC is able to, like I said, implement both digital and analog CDS, and we use a programmable ramp generator that is common for the whole array. There is a single ramp generator that runs through all the ADCs, and it needs to be quite precise to program the start and the end of the slope. I will go quickly, otherwise, oh well, it was okay. So this shows a bit the digital interface. We have counters that can be used also for doing differences. They're optimized for the functionality. And they can be used also as shift registers to bring the data out to the serializer, all optimized for the application. So our company specializes in custom image sensors. So if you have any needs, you can come to visit us, we can discuss your needs, we can figure out how to serve you best with either products we have or with customized versions of the products that we have done.
So much.
Thanks.
Thank you. Do we have questions? We still have 3 minutes for questions. It's okay, no questions from the audience, but I have a question on the slide where you showed where you're using the sensor. So I'm just curious to know what has been, in your experience, the most challenging implementation of the sensor, and why? Where you had a problem statement where you had to implement use the features of the sensor, and then you faced some challenges.
CIS technology or this specific sensor chip? Which one?
This one, the one that you presented with the accuracy of color correction, like accurate colors, representation of accurate colors. That one.
The biggest challenge to come is the hyperspectral version, because we have a spectrometer every 16 millimeters. So we have 96 spectrometers or 48 spectrometers, and all the spectrometers must be in tune. And this requires some smart engineering, like closed loop calibration, spectral calibration with laser lines, tricks like that. Yes. maybe a piezo tripod for adjusting during operation. It's very easy to build a single channel spectrometer. It's much more complicated to build 96 spectrometers in one housing.
Okay, okay. Then I was just curious about that one point. We can, I think, move on to the next speaker. Thank you so much, but I'll be glad to be on your booth and ask some more questions. Thank you. So the next one is also pretty interesting, but I have almost no knowledge of how it works, but we will find out together, I think. The topic is all-in-one auto DL vision software from model to data-centric features. The speaker is Honsuk Lee.
Yes.
Perfect. I have absolutely, please.
Okay.
Absolutely no idea about what AutoDL is. So maybe before we start, you can just give a small introduction to what AutoDL actually is, and then you go into your presentation when it hits. It already hit, actually. You can start.
Yeah.
Maybe it already includes some introduction.
Yeah, but I can tell you first, like AutoDL stands for the auto deep learning. Yeah, DL stands for deep learning, but the title is too long, so we just write down in DL.
Sure. Okay.
Yeah,
now
yeah.
I understand. Okay.
So now today I'm gonna talk about like the deep learning things, the all-in-one AutoDL vision software from model to data-centric features. So I'm Hong-Sung Lee from New York. So today I'm gonna talk about so many things about like model-centric and data-centric. Let me go through one by one. But before I start, I want to give you one question. What do you think of the end goal of the deep learning vision inspection? Because nowadays, many people are talking about deep learning, AI, but of course, it's a big trend, but why should we use this? It's not a mandatory, actually. The reason we want to use deep learning in this machine vision area is, of course, to maximize the inspection accuracy. Without deep learning, without AI, sometimes for some project, we cannot maximize the accuracy. So that's why many people are talking about deep learning and AI. Then we have to think about how to maximize the accuracy with deep learning. That is the most important question we have as a deep learning software suppliers. So to solve these problems, actually, we can think of two ways. One is the model-centric way, and the other is the data-centric way. So today, I'm going to talk about these two things at the same time. For the model-centric features, I'm going to talk about auto deep learning, auto DL models. And then data-centric things is about the labeling things and the synthetic data things. So let me go through one by one. So firstly, the first model-centric feature is the auto deep learning algorithm. So auto deep learning algorithm is actually optimization algorithm when you train the models. So nowadays, many people are just using open sources, well-known model, but that is not optimized for your training data. So if you have an easy task, you can just solve it with that. But if you have a very difficult project, it's very difficult to maximize your accuracy. So that's why we develop auto deep learning algorithm, which optimize three things: deep learning architecture itself, hyperparameter of the architecture, and lastly, data augmentation. So thanks to this auto deep learning algorithm, we can optimize your deep learning model based on your training data so that we can maximize the accuracy of the model. And of course, another good thing is that non-expert of deep learning can easily create the best performing deep learning model because they can just rely on our optimization algorithm. So based on this auto deep learning algorithm, we are providing 9 types of the different deep learning models, from basic classification segmentation to like the deep learning based OCR, patch classification for high resolution, and 2 different types of the anomalies. As you can see, I'm going to go through 4 models today: patch classification, GAN model for the defect generator, and 2 different types of the anomalies. So let's go to firstly talk about 2 different types of the anomaly models. Then, why should we use these anomaly models? Because in the real world, in the manufacturing lines, it's very difficult to gather some defect data, and it's very difficult to gather well-balanced defect data. Because in some cases, some type of defect just occur maybe once in a year. once in 6 months. In that case, we cannot train that defects. That means we cannot train the well-performing deep learning models. So we have to solve this problem. And also, normally, if you only have a regular type of the defects, you can just go with the conventional rule-based algorithm. But the reason you want to apply the deep learning is there are so many non-standard and irregular defects. So to solve this problem, maybe we need anomaly models. So normal models, what we call the supervised learning, we train both normal data and OK data and NG data. However, for these anomaly models, we only train the normal data. That's why we call it unsupervised learning, or some people say it's a weakly supervised learning. So we only can gather some OK data and train the anomaly models. Then the model will find out abnormal cases. So this is a good thing of the anomaly models compared to the conventional, like the supervised learning. So we provide 2 different types of the anomaly models. One is the anomaly classification, and the other is the anomaly segmentation. So the result is very similar, like supervised classification and supervised segmentation, because anomaly classification shows the heat map, which can call class activation map, and anomaly segmentation shows the exact blobs on the defects on the surfaces. So the good thing of this anomaly is you can train even when the defect data is insufficient. And also, you can minimize your resources for the model training and the image labeling as well. Because we train only with OK data, that means we don't train the defect data. So it also minimizes your training time. And also, we don't have to label for the defects because we only have OK data. So this is another good thing of the anomaly models. So we have many use cases of anomaly models. This is just one example. So we want to find out some missing pallet under some logistics centers. Normally, they have to have like 5 pallets. But sometimes, very rarely, they just put 4 pallets in some way. So with this anomaly detection, anomaly classification, we can improve our accuracy from 48% to almost 100%. Is one of the use cases we can share. The next thing we want to share is the patch classification model. So I think you know the normal classification model. But when we train the model, classification model, the basic unit is just the image itself, so that sometimes if you're using the high resolution data, then you have to resize the images into maybe 1024 by 1024. But if the defect is too small, then maybe we lose some data, we lose some defect information. So in that case, we have to think about how to deal with this situation. And also, we can just think about, OK, the image is too large, then maybe we can just divide it into patches like this. But however, if the defect is a little bit large, then maybe defects also occur into the borderline of the patches. Then also, it's also hard to detect. So we have to think about how to deal with these problems. So patch classification is overcoming this kind of limitation of the classification when we are using high resolution data. So what we do is, of course, we divide patch by patch, but internally, there's another algorithm to make it balance, even if the defect is located between the borderlines. So this is how we work with patch classification. You can do the labeling with patches. Just click it or drag. Or you can make it much faster like this. So you're going to drag and do the label on the defect patches. I think, yeah. And then it's done for your labelings. So you can do the labeling as like the segmentation, but it's a classification. So when you're using this patch classification, another good benefit is it's very easy to integrate. Because without this our patch classification, you have to use some pre-processing or post-processing to do the integration with the high-resolution data for the classification. But this patch classification includes all the pre-processing and post-processing of the patches. You just call our model, and then you can get all the result at the end. So we also have many use cases because if you're using high resolution data, then patch classification is very useful. One example is detecting the wire defects, because they want to use a very high resolution camera, like line scan camera, so that we have to detect the defects on the wires. So in that case, like the wires are a little bit in the strange way, so we cannot use the segmentation. We have to use the classification, and then this patch classification helps a lot. So thanks to patch classification, we can increase our accuracy from 66% to almost 99.9%. So there are many use cases with the line scan camera of our patch classification. And I just talked about like two model-centric features. One is anomaly models, and the other is the patch classification. Let me go to the data-centric features. And first thing is the synthetic defect image generator based on the GAN model. So why we need this kind of image generator? Because normally in the manufacturing lines, we are lacking of the defect data. It's very easy to gather some OK data, but sometimes we are having a hard time gathering some defect data. So that's why we are thinking, why don't we generate the defect based on the deep learning models? So we are using the GAN model. GAN stands for the Generative Adversarial Network. So in the GAN model, there is two networks. One is the generator, and the other is a discriminator. Generator just generates the new data, and discriminator will discriminate. This is very similar with the real data, or this is a little bit different from the real data. So the model will find out, model will create the new data, which is very similar with the real data. So this is how a GAN model works. So to teach some types of the defect, we need at least 10 defect data. So with the 10 images of defect, we can train the GAN model. Then after you train the GAN model, we can use the OK data and then put the defect stamps on the GAN images, OK images, and then a GAN model will generate some new defect images as like this one. This is how it works. Yeah. And also, sometimes, if GAN model is a little bit heavier model, as I mentioned, because it includes generator and discriminator, right? So that it's also difficult to use high resolution images. So we also have a patch mode to this GAN model, so that even if you have a very small, tiny defects with high resolution data, you can use a GAN model. This is another benefit of ours. And also, as I mentioned, we only require 10 defect images. So you can easily create some GAN model with little amount of the data. And also, we provide a stamp tool. So you can put these defect stamps on the OK data, on the surface of the OK. Then these defect stamps will be very similar with your original defects. So you can easily create very similar artificial defects with real defect data. So by using this GAN model, we can generate the synthetic data. And of course, compared to the, how can I say, initial data set, without this synthetic data, we can improve the model's accuracy, like up to 97% on this case. And lastly, I want to talk about some AI-based labeling tools, because nowadays, many people are using large amount of data, more than like 10,000 data images. In that case, labeling is a very, very time-consuming job for you. So we invented AI-based labeling tools. So there are many AI-based labeling tools, like we call it like the magic wand, auto-selector, or keyword labeler. Let me introduce first about the auto-selector. Sorry. Sorry, I think the video doesn't work. So anyhow, yeah, auto-selector is like, oh, it works? It doesn't, something like, yeah. So it's based on our foundation model. If you just click and drag, then it can easily tell where you have to do the labelings. I think if I can show the video, it's much easier to understand. But yeah, if you're interested in, please come to our booth. I'm going to show it later. So auto-selector is like you just click or drag, then the labeling is done very automatically. This is the biggest benefit of auto-selector. And we also have the keyword labelers. The video doesn't roll again. Yeah, you just type in the keyword. Like I want to find out some drops on here. You just write down the water drop. Then our foundation model will find out the water drop on the images automatically. So thanks to this auto selector or keyword labeler, you can easily do the labeling without any manual labeling tools. And lastly, we also have auto labeling. This concept is a little bit different from the previous one, because auto selector and keyword labeler, we are using the foundation model, but auto labeling is like this. So just assume that you have like 10,000 data, and then maybe you can do the manual labeling for 50 images or 100 images, and then we are going to train the one deep learning model for the labeling purpose. And then once you create some one deep learning model, you can use this deep learning model's features to do the labeling for the rest of the 9,900 images. This is the concept of the auto labeling, and it's also very powerful when you have a large amount of the data. So what we do is we try to minimize your resources for the labeling, because sometimes labeling is really, really time-consuming job. So let me summarize my presentation today. So we are providing auto deep learning vision software to maximize your accuracy. Some problems here. Yeah, so and then we have a two software package. One is the training software, and the other is the runtime library. So with our training software called NeuroT, you can upload your data, upload your images, manage your data, and then do the labelings, and then train the model, and then check the model's result and performance. And once you are satisfied with the model's result, you can easily export that model, and you can integrate this model with our runtime libraries. So this is a concept of NeuroT and NeuroR. So T stands for the training software, and R stands for the runtime libraries. So all this, our software package is based on the auto deep learning algorithm, as I mentioned, which optimize deep learning architectures and hyperparameters automatically. So even you're not the deep learning expert, you can easily creating the best performing deep learning model just with one click. So I just assume some typical cases. So if you don't have defect data, you can think about using our GAN model, which generates the synthetic data. If you are using very high resolution images, then you can think of using our patch classification. And lastly, if your defect type is really, really irregular, then maybe you cannot go with the supervised learning. Then we also provide two different types of the anomaly models, which solve your problems on the real manufacturing site. So I just summarized my presentation today. Our company name is Neurocool from South Korea. Our booth is over there at 8B11. So if you have any questions, unfortunately, I cannot show you our very awesome label tools like auto selector or keyword labelers. If you're interested in, please come to our booth. Thank you very much.
Thank you so much. So do we have questions from the audience? No questions from the audience, but I have a few questions. It's very interesting. So the unsupervised models are the ones that you're calling anomaly models, right? The anomaly models are called anomaly models, but the images that are used to train those models are not actually of anomalies. They are of the ones that don't have the anomalies, right?
I didn't get it clearly. What do you mean? Yeah.
You said that in your you make your anomaly models with the help of the good images, only good images.
Only good images, yes.
And not okay images.
Not okay images.
So those images, they don't actually contain any anomalies. They are not. They are the ones that do not have anomalies. They are the right data.
Yeah.
But the models are called anomaly models, even though they are trained with good images.
Yeah, because anomaly models learn the boundary of the good images.
Okay.
Because if there's image data, we can calculate this image data and then put this image data into some very multi-dimension space. And then once we embedding those images into those images into space, then we can tell where the boundary is, right?
Okay.
Once we calculate this boundary of the OK data, then if there's new images come, then we can embedding once again and then see whether this is in the boundary or out of boundary.
Okay.
If this is in the boundary, we can consider it as a OK.
Okay.
If it's out of boundary, we can consider it as a anomaly, abnormal cases.
Yes, exactly.
Yeah, this is how it works.
And then how do you use the anomaly models for classification? Because that is also what you said, right? You're using the anomaly models to classify the anomalies, like the type of defects that can be there or which look similar or something like this. You can classify the types of defects using the anomaly models.
No, by using anomaly classification, we only can classify whether this is good and bad.
Okay.
If you want to classify the defect types, then of course we have to go with the supervised classification.
Okay. And then you said that for your supervised classification as well, then you have the other side of the software suite, which can generate images that can be used by the supervised learning algorithms. So for the supervised learning algorithms, you need labeled data.
Supervised learning?
Yeah, for the supervised learning.
Yeah, we do labeling, whether like we tell this image is class A, this is class B.
Yes, exactly.
We do the kinds of labelings, yeah.
So those labelings, I mean, that labeled data is needed for the supervised learning to work, right?
Yes.
And you said at the later point in time in your presentation that that AI can also be used to generate these defective images.
Yes.
To label these defective images, and then you can feed it to the supervised learning, and then that's it, right?
You're right. So if you only have 10 defect images, of course we have to do the labeling for those 10 defect images, but we can train GAN model with these 10 defect images, then we can generate a lot of the synthetic data, defect data. Yeah, you're right.
Great. Thank you. I'll meet you at your booth. I have more questions, but right now we have to go to the next session. So,
thank you very much.
Welcome.
Thank you.